So this diagram should look pretty familiar at this point. We've spent a lot of time trying to think about how the magnetron works to help heat up food inside the microwave. And last class, most students made a lot of progress with this reading, writing down things that either connected to what we've seen before in class or extended their thinking or seemed challenging or puzzling. If you didn't finish this, I kind of gave folks an extension over the weekend, and this is something that you can work on today as well. I will not put final grades into the grade book until the end of the class today, but most students should be working on going further. Before I show you that, I just wanted to shout out all the people who helped us update this diagram to make it more complete. You can tell there are names of a number of people in class who have helped us figure things out, including Ray and Cameron and Malik and Finn and Kira and Max and Ronan and Khadijah. I'm probably missing some folks, so if I missed you, I apologize. But this diagram shows us what our class can do together when a whole lot of people are thinking about a complex question. Speaking of which, your work for today is related to this process. How the interaction between electric field and magnetic field can cause waves to move through space from the microwave magnetron to the food particles. And in order to understand that, we're going to use a simulation about radio waves. So you're going to go to Schoology and open a document called Radio Patterns. The document's going to look like this, and you'll see there are a number of different rows and some specific instructions. There is a claim at the top that came out of students' models. I kind of tried to take a bunch of people's ideas and put them into consensus words. So the claim here is static, aka unchanging. Static means unchanging. Electric fields alone can't explain how the magnetron antenna heats up food particles. We need to understand how the electric field changes in waves. There are some instructions here that give you a link to a simulation that I will show you in just a moment. It says radio waves are similar to microwaves, but they work on a different scale. We are going to work through this simulation to help us understand how the evidence connects to our ideas about how the magnetron heats up food. For every row below, choose the exploration settings carefully. Those are these settings right here. And then record observations as evidence. So you're going to do these two boxes for every single row. These two boxes, these two boxes, these two boxes. That's sort of like the basic beginning of how you get started with this work. You're going to complete all focus questions. There are 3, 1, 2, and 3. And then for at least 2 rows, you are going to be completing the analysis question. So basically the analysis question is, how do these observations connect to your understanding of this claim? What questions or what answers does it bring up? So for example, let me show you what it would look like to get started with this. If I go to the simulation, it starts out looking like this, but I need to be very careful to select the setting in the exploration here. I can just go ahead and try stuff. It does all kinds of weird, crazy stuff when I just go in and press buttons, but that's not going to help us make as much progress as doing a focused, careful exploration. So we're going to start by changing the field displayed to a static field. Remember, static means unchanging. And if I go down here and click static field, you'll notice I get something that's pretty similar to that other simulation that we looked at, where we can see the arrows from the electric field near an electron change as I move the electron the arrows change in length and direction, and the farther I get from the electron, the weaker the electric field is, the shorter the arrows are. So this is what we're looking at first, and this says, what do you notice when you move the antenna electron up and down with the new settings on the left? So you would want to start by just writing down some things that you see. The arrows change length, the arrows change direction, and the arrows get weaker as we get farther away from the electron. If we wanted to, we could answer this question here, but you only have to answer 2 of them total. So after you've recorded some observations, you would then go on to here and change the settings to transmitter movement equals oscillate. I'm going to keep this static field, but I'm going to only change this one section. So I will change this to oscillate, and we're able to change the frequency and amplitude here. So I could even like go in and like make those changes and see how they affect what's going on here. We do know these words from previous explorations. And you might start noticing some stuff like this electron over here is wiggling, although it's not wiggling at the same time as this. These are important observations to record, and this probably would be a good place to answer this question. How does this influence your ideas on the claim above? If you have questions, I strongly encourage you to ask other people in the classroom. There is often an assumption that when a substitute is in the room, you don't really have to do all that much because we'll just get more time to do it later. That is not the case today. You absolutely need to use your time to be successful today. We will not be getting more time to do this in class. We will review some of the ideas, but if you don't make progress with this in class today, you will have to do it outside of class, and it will be more difficult, not easier, if you don't have other students in the room who you can ask questions with. So again, you should have at a minimum these things done. For every row, do the exploration, record some observations, and complete all focus questions for at least 2 rows, completely analysis questions.